Hello programmers. Today in this tutorial I would like to discuss a little bit of how Coder's Basilisk's macro programming system, its metaprogramming system I should say, because it's not just macros, it's true metaprogramming, differs from that of Rust, Nim, and Lisp. Now, I will confess that when I talk about the Rust, Nim, and Lisp, which are like the kings, basically, of macro metaprogramming in the programming world right now, I'm going to be a little bit ignorant of some of the finer details, but I studied things a little bit, right? And according to what I know, they lack the critical features that I'm going to show you here in Coder's Basilisk today. So before we talk about those other languages, let's talk about this little demo here. In this little demo, what we have here is we have an empty CodeGen main function, so we're not generating any actual code here. And we just include the meta library, standard meta. So this is just a bunch of CodeGen code. There's no code generation at all. We're just basically testing out parsing and stuff. And what we have here is we have this little function defined, right? We're going to declare it public, right? Not that it matters, right? We have this function here, myCoolFunction, which receives 3 random-looking arguments. You know, let's make this a little bit. Let's make this a little interesting. Let's make it more interesting. There we go. We have this cool little function here. And all it does is it basically defines some variables. We have an if statement, some more variables, an expression statement, a label, and then we call this parsehook here @inspect. And what this is going to do is at parse time, this is going to call a function, this function up here, this really big one. This token right here will be consumed, and then the rest of the compilation unit will be parsed by the parser as one would expect. Okay, so let's look at parsehook inspect. Right, the code up here, by the way, just prints out a type, right? A type in the language, right? This is the AST node for a type. Okay, so here's parsehook inspect. This function is literally called at parse time. Let me make that very clear, guys. And actually, there's a way I can illustrate that. Let's put return 3, and let's have it return hit. Okay, there. Anyway, so now there's a return statement here. You're going to see that that this is not known by this because this is invoked here before this return statement is parsed. But back to what we were talking about. This function is called during parse time. The first thing it does is it gets the AST from the compiler, right? The parsed AST. Then it gets the symbol that the parser is currently working on, active function. And what it does is it prints out some metadata about this function. Its name, whether it's public or not, whether it's incomplete or not, whether it's CodeGen or not, whether it's pure or not, and whether it's no export or not. Then it prints out its arguments. Either no arguments, or it goes through its arguments and it debug prints them, right? And they're just type structs, so it just debug prints the types, which includes the names, right? It's stored in the member name field right here. Then it goes through the scope stack. This is the list of scopes that are currently visible from the current scope, right? And it goes through every single one and it prints their local variables. Then it looks at their last statement, right? If there is a statement within the scope, it looks at it. Let's do this, right? I just wanted to do that for demonstration purposes, right? It looks at if there are statements in that scope, which I mean, unless the only scope that could possibly not have any statements is the innermost scope, right? So if I put @inspect wiggle right here, right? But anyway, that's not important. Anyway, if there are statements in the scope, it prints out the last statement in the scope. And it prints out the type of the statement, right? It says whether it's a bad statement, a NOP, an expression, etc., right? So this is basically demonstrating that we have full context of what we're doing when we invoke this parsehook, right? So let's run it. And here's the printout. The active function's name is myCoolFunction, right? That checks out. It's public. It's not codegen. It's not pure, and it's not no export. It has these arguments: f32u, float u, yeah. myCoolStruct, a struct with 3 members. Pointer indirection level of 1. Yeah. Encoder's Basilisk, and if you try to pass a struct by value into a function, this gets turned into a pointer. So that's why it's pointer with indirection level of 1. ZZZ, yeah. And then double QQQ, which is an F64. Then there's the scope stack, all visible variables from the deepest backwards, right? And so the innermost scope right here has 2 local variables, X and WeMoac, and the last statement is a label statement right here. This statement here. This is a label statement. This is how labels look in Encoder's Basilisk. Then outside of that, there's a scope with 0 local variables, this while statement here. And the last statement in it is an if statement. That's this statement here. Then outside of that, there's a scope with 4 local variables. cbas_retval, this is an internal variable. It's i32, it's just the type of the return value. i32x, that's this variable. f32y, that's this variable. And then f64, pointer, 4 levels of indirection. Array length of 37, z. And the last statement in this scope is a while statement. As you can see, at the time that this parsehook is invoked, this return statement hasn't been parsed. So the last statement in this scope, in context, is this while statement. And then here's the rest of the compilation unit's tokens. We have read-write access, wiggle, right here, this token right here. Then we have 2 inds, the return keyword 3, int xxxx, right here, semicolon, fn codegen main, colon, in. And that's the entire rest of the compilation unit. So what we have access to here, right, is we have access not only to the to all these tokens at the time of this invocation, right, and we can modify the token list however we want. We can consume tokens. We can take the tokens in the token list and completely replace them with a new set of tokens. So if I do cg get next, right? This will return the value of the next variable, which is what peak looks at. This is going to cause a compilation error because what this is doing is it's basically deleting all the tokens after this, right? Uh-oh, unexpected end of compilation unit. Yeah, see this, we're actually taking the actual compilation unit and we're taking the actual next variable, which is the variable that holds the pointer to the next token in the linked list. And we're setting it to null, right? We're basically saying that there are no tokens left in the list, right? We could insert any tokens we wanted here, right? We could take all of these tokens and completely replace them with anything we wanted. We can read these tokens, we can modify these tokens, right? So we are, when you invoke a parsehook in Encoder's Basilisk, you have complete access to the AST, you have access to internal variables in the parser, and you have contextual knowledge, right? You are able to, extend the language meaningfully, right? You're able to, and you're able to access, by the way, types too, right? I can look at these types, right? You see here when I debug printed a type, I can go through the AST, I can go to the type table here, and I can find out how many members it has. And of course, I can access the type of these members. I can even modify the AST during the parsehook invocation if I wanted. I could add a new member to the struct if I wanted to. That's something I could do. And so that's that, right? So parsehooks in Encoder's Basilisk are super powerful, right? They properly extend the compiler, right? Now we're going to talk about other languages, right? First of all, we're going to talk about procedural macros. And hold on, I'm going to actually bring up Claude because I'm going to actually ask it questions because it knows how to code in these languages, and I don't know Rust or Lisp or Nim, right? So anyway, in Rust, as I understand it, Rust's procedural macros do not have access to the full token list of the compilation unit. That's one. And two, they do not have the ability to access the wider AST, right? So if you see here, Rust, what the argument that you receive is a token stream. What this is basically just a sequence of tokens that was passed inside of curly braces or parentheses or whatever to the macro. Then it returns a token stream, which basically this right here is emitting a sequence of tokens, which gets written here, right? This text here gets inserted right here, right? And it won't be text; it'll be Lexer tokens, whatever, right? This is being parsed into Lexer tokens, or whatever, AST, or I don't know, and then I don't fucking know what this does. I've seen this function get used in Rust all the time. I don't know, right? In Lisp, of course it's Lisp, right? So obviously Lisp macros are kind of complicated, right? But basically Lisp macros are kind of limited in many of the same ways. Macros in Lisp, they accept a sequence of tokens, right? A sequence of atoms or whatever these are called, these things, right? And parentheses and whatnot. And you can kind of interpret them however you want. And then there's a sequence of commands you can do to create variables and stuff. But you can't access the wider AST, I don't think. I don't think you can access the list of symbols. I don't think you can access the full compilation unit, right? You only get the sequence of tokens you passed into the Lisp macro, right? And so Lisp macros are quite limiting too, right? They don't give you the same contextual knowledge from the invocation point that Coder's Basilisk parsehooks do. Then there's Nim macros. And I don't know why people say Nim macros are so powerful and interesting, because the thing is, yes, you do get to work with the AST in Nim. But it looks like all Nim macros actually allow you to do is it allows you to take a parsed AST, parsed by the main parser, feed it into a Nim function, and then have it generate a new AST and then spit it back out. So it's just AST to AST transformations. And I'm not even sure that it gives you access to the full AST of the language. So anyway, I confess I'm a little ignorant here, so we're going to ask Claude. Hey Claude, say hi to YouTube. I'd like you to explain for each of these languages, Rust, Lisp, Nim, I know so little about Nim that I don't actually know here, right? Can the macros / compile-time code access the full list of tokens left in the compilation unit? Access only a portion in the compilation unit. For instance, tokens inside curly braces or parentheses passed to a macro. The surrounding scopes at parse time during parsing. can insert replacement tokens. All right. Yeah. And so anyway, let's ask Claude. So anyway, we're going to find out from Claude here, and Claude will probably tell us the right answers, whether or not these languages have oh crap, this is poorly formatted. We might have to ask it again. Hopefully it's able to figure it out. Okay, so anyway, let's read this. These three systems have meaningfully different power levels and access models. Let me go through each language against your 5 criteria. Full unrestricted token list. No. Proc macros are a sandbox. They only see that's it, right? So in Rust, you can't access the full token list. You only get to the sequence of tokens you pass to it. Only a portion of tokens? Yes. Right? It's the interior tokens right here, right? Derive macros get the item they're applied to. Interesting. So, okay, so attribute macros get their args plus the annotated item, nothing more. Surrounding scope access, no. So you can't get the context, right? Proc macros run as a separate compiled binary and have 0 semantic information. No types, no variable bindings, no enclosing scope. So you don't have any context in Rust of the surrounding code. You have no knowledge of it. You can't meaningfully extend the compiler. At parse time, sort of. They run post-tokenization during the expansion phase before type checking and full semantic analysis. Yeah, which is pretty similar to when parsehooks are invoked in Coder's Basilisk. Yes, they return a token stream that substitutes the original invocation. So, yeah, so if we look at Rust procedural macros, what they do is they basically are tokens in, tokens out, and that's it. You don't get access to any contextual information. You don't get access to the AST, none of that. Lisp. There's actually 2 macro layers. I actually didn't know that. Full unrestricted token list. No, the macro receives only the form it was invoked with as unevaluated S expressions, right? So you get the little atoms, right? Which are basically tokens in Lisp. Only a portion? Yes, exactly. The subforms passed as arguments. Right, so that's what you get. Surrounding scope access? Partially. So you do not get access to everything. Common Lisp has the and environment parameter, which gives macros access to the compilation environment. Enough to query what macros/symbols are declared, whether a variable is special, etc., but not full lexical scope or variable values. So yeah, so it looks like there is some amount of stuff you can do with Common Lisp, accessing like the list of variables that are declared, but you can't look at all the scopes and stuff. At parse time, no. After reading, before eval/compile. Lisp's read phase turns text into S expression, lists. Macro expansion is a separate later phase. Okay, so that's interesting. I don't know if that is equivalent to what Coder's Basilisk does, or if that is just, or if this is a step down. Either way, this definitely is a step down because of this, right? So Lisp macros are inferior to Coder's Basilisk macros because you don't have access to everything. Can replace tokens? Yes. The macro system returns a new S expression that splices in place of the old one. This is the core of the system. Code is data, right? So that's basically like, so you can do that, right? So this is very similar to Rust's procedural macros in that you take tokens in. Instead of tokens, it's an S expression. It's S expressions or whatever. And then you spit out new tokens, right? New S expressions. And then there's a new, another kind of macro system. Full unrestricted token list. Yes, uniquely powerful. So this is closer to Coder's Basilisk's parsehooks, right? Because this parsehook has access to all of this. We can read all of this, right? The reader macro has access to the full token list. Only a portion, they self-delimit. They consume what they need. So that's exactly what Coder's Basilisk parsehooks can do, right? You usually write your parsehook so that it self delimits. It takes out the portion it needs, hold on, standard meta slash like the worksheet here, right? What this is doing here, by the way, is this is some metaprogramming code I wrote which defines the worksheet, basically macro system, right? So you see here, this parsehook here takes some arguments, right? It takes this, and then it eats this. And so this is self-delimiting, right? It takes out the portion of the set of tokens in the token list it needs. But reader macros in Lisp do not have access to the surrounding scope. No, the reader does not know about scope. So basically, it looks here like the way Lisp reader macros work is they just are sort of a thing that happens before the parser. At parse time, yes, literally during reading. This is the earliest possible intervention point. Let's actually ask Claude about that. Hey, Claude, could you clarify for me here something about Lisp reader macros? Do they happen before any S expressions are parsed by the main parser at all? Or are they sort of like in the middle? How does that work? Do they any contextual information at all? Or are they see what they say. Nim has a richer... Okay, we'll talk about Nim later. Let's first ask about Lisp. Really quick. Hey, Claude, could you clarify for me here something about Lisp reader macros? Do they happen before any S expressions are parsed? How does that work? Do they have access to any contextual information, or are they just tokens in, tokens out? In the middle. Okay, so that is similar to Carter's Basilisk in a way. Lisp does not have a separate lexer pass followed by a parser pass. The way most languages work, there is no first tokenize everything then parse. Instead, read is a single recursive character by character function that constructs S expressions on the fly. This is interesting. Reader macros are dispatched at the character level mid-read inside this recursive descent. Interesting. When the reader hits a macro character like this or whatever you define, it immediately calls your function right there in the middle of constructing whatever outer expression is currently being built. Your function then has control of the stream, can call read recursively itself, and returns an S expression that gets handed back up to whatever called into your macro. Interesting. So it looks here like what it does is it basically just takes the rest of the compilation unit, it'll consume whatever you want it to, and then it emits S expression code to replace the portion of the text that you consumed. So it's not before any S expressions are parsed. Outer S expressions may already be partially constructed when your reader macro fires. It's more like reader macros are woven into the fabric of the read process itself. That's interesting. Do they have contextual access, or are they tokens in, tokens out? They're not purely tokens in, tokens out, but their context is narrower than you might hope. Here's exactly what a reader macro function receives and can see. Right? Defin my reader macro stream char. Right? So this is the, I guess this is like the access to the token stream, which you can call read on or something. The input stream char equals the character that triggered this macro. What they can access, the input stream, fully parsed sub-expressions. They can call read recursively on that stream, getting back complete expressions. So they can kind of interact with the main parser. They can ask the main parser to parse an S expression. I think that's what this is saying here. Dynamic special variables. Since reader macros are just Lisp functions running at read time, they can read/write any dynamic var. This is actually how reader macros can communicate state with each other. Okay, so they have access to like some global state. The current read table, also a dynamic variable. A reader macro can even modify the read table mid-read, affecting how subsequent characters are interpreted. Okay, that's interesting. Okay, so they cannot access what has already been parsed. No reference to the partial AST. So that is something coders Basilisk can do that Lisp metaprogramming cannot do. They don't know they're inside a list or what came before them in that list. That, as you can see here in our printout here, when we invoke our @inspect, we're able to see that we're inside of a while statement, a last statement. We even see the last statement written was a while statement in this one. Then there's an if statement in this one. Then there's that label statement immediately before the @inspect macro invocation, right? And we can see all the scopes and all the local variables. And of course, we can see the global symbol table, which is how we found our function and our information about it, and our function arguments. So yeah, the interesting emergent consequence. Because reader macros can call read recursively, they can consume structured input, not just raw characters. Okay, so that's kind of like nim, I guess, right? So with nim, you get access to parsed AST stuff, right? Backwards blindness. They have a window that looks forward into the stream and downward into their own subreads, but they have no rear view mirror into what's already been read above them. Yeah, so that's very bad. Anyway, but now let's talk about nim, right? Let's talk about nim. nim has a richer compile time story than either of those. A key distinction is untyped versus typed parameters. Full unrestricted token list. No, but closer than Rust. Macros receive the AST nodes of their arguments. There's no mechanism to grab arbitrary tokens from elsewhere in the file. However, macro pragmas applied to whole procedures can transform the entire body. So it looks like you get the AST. It doesn't look like you get actual tokens. Only a portion? Yes, the AST subtree of what was passed. With untyped params, you get raw pre-semantic AST. I don't know what that means. With typed params, you get semantically resolved AST, including type information. Okay, this is a bit confusing. So it looks like you can choose the level of semantic analysis you get here. Surrounding scope access, the strongest of the three here. Typed parameters can carry type semantic info. Bind sim lets you resolve symbol names in the call site's scope. Interesting. But it looks like, does it actually let you access the full AST? I'm gonna have to ask us about that. At parse time, no. Macros run during semantic analysis on the already parsed AST. So this is after parsing. It's not during parsing. Can replace tokens? Yes. Macros return a nim node AST fragment that replace the call site. Okay, I have some questions about init. Right, let's scroll up here. You talk about how nim gives surrounding scope access, but can it read and modify the full parsed AST up to that point? Can it access every single function, variable, and scope in the compilation unit? Can the scopes currently being parsed? The stack of scopes. Let's ask it that. So because I'm wondering here if that's true, right? So nim, basically what it does is it provides, I guess, you give it some AST nodes. You give it some nim code, right? You can't write your own language. You give it some nim code, and then that AST gets passed into a function. You get to do some transformations on it and make a new AST node. Can a nim macro read modify the full parsed AST up to that point? No, a nim macro does not receive a reference to the module's AST. So this is something coders Basilisk does that nim does not do. It receives, because as you can see, oh, pulled the wrong thing up. As you can see in our little demo here, where is our demo? td reflects.css, we are able to literally grab the AST, grab the type table, and then print out the name of a type and a number of members, right? We're able to, in here, grab the symbol table, look up this current function that's being parsed, and print out information like, is it public, is it incomplete, is it codegen, is it pure, is it no export? Yeah. Can a nim macro read modify the full parsed AST up to that point? No, a nim macro does not receive a reference to the module's AST. It receives only the AST subtrees of the arguments passed to it. There is no give me everything parsed so far in this file handle. What you can do is reach out to specific named symbols using getImpl. Fetches the AST of a specific symbol. So interesting. So you can sort of access the symbol table, but that requires you to name what you want. You're pulling a specific thread, not reading the whole tapestry. You cannot enumerate or dump the full module AST. Interesting. I wonder if this... Oh, okay, I see. Okay. Can it access every function, variable, and scope in the compilation unit? No, not by enumeration. There is no API equivalent to give me all symbols currently in scope. You can look up a specific named symbol with bind sim if it's visible from the call site, then call getImpl on that to get its body AST, inspect type info with getType, getTypeImpl, getTypeInst on typed arguments, but that's pull by name, not push everything. There is no getCurrentScope that hands you a list of all bindings. Okay. And as you recall, guys, we do have getCurrentScope. We can look at the scope stack directly, and we can just look at the top of the scope stack, and that is the current scope. So that's something my language can do that nim cannot do. Can it see the stack of scopes currently being parsed? No, this is the sharpest limitation. When a macro fires mid-parse, the surrounding partially constructed scope, the enclosing procs or local variables, the outer blocks bindings, is not exposed to the macro. The macro cannot see what local variables exist in the function it's called from, the partially built AST of that enclosing function, any notion of what scopes are currently open above me. So what did I actually mean by strongest scope access? I should clarify that. The type versus untyped distinction is what earns nim that label relative to Rust and diff macro Lisp, but it's more modest than it sounds. Raw pre-semantic AST. Yeah, so anyway, this seems very, very limiting, and I honestly don't understand what the usage of it would be. In nim, is it possible to write your own parsers at compile time, like you would in Rust procedural macros, and which is possible in my language? Or is it? Are you limited to only valid nim syntax? So let's ask that. Anyway, so I can't guarantee, guys, that this is not hallucinated, but this should be correct, right? And this should tell us whether or not Coder's Basilisk is really, truly special here, right? It seems so far that these three things, right, which are basically supposed to be the kings of metaprogramming, are basically, trash compared to Coder's Basilisk. In nim, the full nim parser runs on macro arguments before your macro ever sees them. The macro receives a nim node. You are locked into valid nim syntax. So you cannot write new syntax in nim, according to this, right? The workaround, string literal DSLs, right? The escape hatch people use is passing a string literal and writing a custom parser inside the macro body. So you could write your entire language inside of a string literal. But that would be shit. I hope you understand that, right? Coder's Basilisk does have a similar thing to this. I have built-in read file. You can read a file byte for byte. Okay, yeah. Anyway, so now let's talk about what Coder's Basilisk has that these languages do not, right? In Coder's Basilisk, we literally have access to the actual AST nodes of the parsed compilation unit. We have access to the actual parsed AST, the list of types. We can access metadata of the types, their name, the number of members, whatever, right? We can modify it. We could take n members and then assign it a new value. td.nMembers equals 473. If this actually was allowed to continue to compile, it would cause an error, but whatever. it'll work. It won't, because we're not actually doing code generation, it'll be fine, but, we're able to edit the AST right here. We are able to look at the list of scopes that are visible to us at the call site. When we do add inspect here, we're able to see this label statement. We're able to see this if, while, these variables, these variables, these variables. We're even able to see the return value and the secret variable, which holds the return value. We're able to look at information about the statements, right, that are in the scopes, right? Yeah, and then we're able to access the entire compilation unit after this point. We're able to see these tokens. So let's talk to Claude here. Okay, now let me describe to you my language, coders. Okay, now let me show you a sample of code from my language, coders Basilisk. Let's grab this, paste it in here. This is a purely compile-time test file that showcases inspecting the how coders Basilisk has full unrestricted access to the parsed AST, the current context at macro at invocation time function called during the parsing. How does this compare to Lisp, Rust, and right? I'm going to mention this line here. Because the unit is, but in principle, you could. Wasp and nim. Let's ask it. So what we done, we just passed this example here, and we're asking Claude here to just examine what's happening here. It doesn't know the language, but it should be able to sort of figure things out. This is a genuinely remarkable capability set. That's just its sycophancy, guys. Let's move on. Let me go through what the code actually demonstrates, and then do a precise comparison. There are several distinct things happening. Parsehook inspect fires mid-parse inside the live parse stack. Yep, it understands that. The invocation site is right here. And at that moment, it can see the entire scope stack as it currently exists. The function scope, the while scope, the if scope, with all their variables and already parsed statements. Correct, we saw that. This isn't after compilation, look back at the AST. This is during parsing, looking at the live partial parsed state. Yep, that's exactly what we do here. It has a pointer to parser internals, not just a view. CG getNext assigns null directly to an internal parser variable. That's not an API, that's a raw pointer into the parser's guts. I beg to differ. That is an API, but it is also that, sure. The comment says doing so crashes the compilation unit because it breaks the token stream, which proves this is genuine write access, not a sandboxed copy. CG peek plus consume together give read then advance on the remaining token stream, a look ahead consume model applied to everything not yet parsed in the entire compilation unit, right? So you can basically extend the parser just like you write parser code. CG get AXT hands back the live AST object and AST.active function of 0, scope x 0i, and scope 0. It supposes the parser exact internal state as a traversable struct, right? So precise comparison to Rust, Lisp, and Nim. Okay, so let's see if it understands everything, right? Runs during parsing, Rust procedural macros, post tokenize, right? So it's well, I mean, actually, it should be a checkbox here, I think. It's post tokenization, just like Coder's Basilisk is. So I think it's wrong here. This should be a checkmark. Lisp post read. Lisp apparently works character by character or something. Kind of weird. Lisp reader macros check during read. Nim macros X post parse. Access to live scope stack invocation XXXX check, right? So none of these have that. Access to already parsed statements in scope XXXX check. Full AST access. None of them got it except me. Forward token stream read. The only ones that have it are Lisp and then my thing, right? Pass tokens only to Rust procedural macros. Forward token stream, write, modify, X. Indirect via return for Lisp reader macros. And then nim macros, X, raw pointer in Coder's Basilisk. Knows active function being parsed. XXXX, X, check, Access to type table, symbol table, check. XXX, partial named lookup, right, in nim, right? In nim you can look up. You can resolve get impl or whatever it was that it said. Checkmark, direct. You have direct access. Custom parsers at compile time. Checkmark in Rust, token stream in, right? Via reader macros in Lisp. Lisp reader macros, check, right? Obviously, because they have access to raw characters. Nim macros via string literals, which basically, you could do that in any language which has eval, basically. Like in JavaScript, you could use eval to, to write compile time code, which parses a string literal or something. And then checkmark in Coder's Basilisk. The qualitative gap. The three comparison languages exist on a spectrum of macro as transformation. You pass something in, you get something back. The surrounding context is largely opaque. Even Lisp reader macros, the most powerful of the three, only see forward in the character stream. They have no idea what scopes are open above them, what variables exist, what's already been parsed. Coder's Basilisk is doing something categorically different. Macro as parser plugin. Yes, it understands what I'm doing, right? So basically, parse hooks extend the parser. You are not just writing a macro. You are extending the compiler itself. The parsehook doesn't receive arguments and return a replacement. It fires as a subroutine of the parser itself. Ding, 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 ding. With the parser's full internal state exposed as readable, writable data. The distinction is the other three languages, macro runs alongside or after the parser, receiving a curated slice of information. But it's... Yeah, I think this is right. And then in my language, the parsehook runs as part of the parser with a pointer to its live internals. The closest analog in the three languages is Lisp reader macros, which also fire mid-parse and get a stream handle. But reader macros don't know about scope, and they get a character stream rather than a structured token stream with direct pointer access. Yeah, so this is what I'm... Yeah, and then who cares what the AI is curious about? Anyway, so this is... I hope you guys understand now a little bit more the value of Coder's Basilisk. That this is new and interesting computer science, right? That this is useful new technology. that even if you think my implementation is clunky, that even if I ramble a lot, even if my voice is hard to listen to, that this technology is worthwhile, and it's worth learning, and it's worth stealing. Let me remind you guys that this code, this project, is CC0. This is a CC0 compiler. And you can compile it. -O. You can compile it just like this. This works. You can you just compile all the C files together, -O3, -O right? This just makes it fast. /cbass test2/cg reflect. Test2 cg reflect. Yeah, and this works. This is a working compiler. This is something you want in your toolbox. This is the future of programming, assuming that AI doesn't just replace humans, right? Even if AI replaces humans, they're going to need a tool like this. I hope you guys enjoyed. Thank you for watching. I will link I will link you guys this file from the main repository. This is in the main Coders Basilisk repository, so that you can read it. But you can't just go into the repository yourself. I hope you guys enjoyed. Thanks for watching.